Thank you for the introduction. My name is Leo, and this is a joint work with Dorit Aharonov. And don't worry, I'll explain all of those terms, the precise meaning of it one by one. So since this is a general audience consisting of both physicists and computer scientists, I thought I would start by going over some very basic concepts, so excuse me if you're a little bored. I'd like to first review the idea of constraint satisfaction problems in classical computer science, and these are basically classical analogs of Hamiltonians. Classical CSPs are defined on hypergraphs, which we call their interaction graph. And a KCSP is a function that basically takes any assignment of the nodes in the graph to bits and outputs some positive integer characterizing the number of constraints violated. And it can be written as a sum over the hyperedges, where each term in the sum corresponds to a hyperedge containing to at most k nodes. And it is famously proven by Cook and Levin that the problem of deciding whether the minimum number of constraints violated is 0 or positive is an NP-complete problem. Now, Hamiltonians are essentially, in the computer scientist language, quantum version of these CSPs. Similarly, you can define a k-local Hamiltonian, which is a sum over the hyperedges, where each term are now a permission operator acting on less than or equal to k particles. And each particle is now a qubit, or potentially a d-dimensional particle that we call a qubit. And typically, we consider that each term should have some bounded norm. And the maximum value of this term-wise norm, we call the interaction energy. And typically, for a k-local Hamiltonian, there's n to the k number of terms. And again, in most physical contexts, we consider the locality, the interaction strength, and the dimensionality of the particles are considered to be constants. And famously, in 1998, Kitaev quantized the Cook-Levin theorem and show that the problem of deciding, basically estimating the minimum eigenvalue of a Hamiltonian is a complete problem for the quantum analog of MP, which we call QMA. It is also interesting to note that if you only consider two local Hamiltonians on a 2D graph or a 1D line, the problem is still QMA complete. So in our study, we're interested in the transformation of these quantum CSPs, which we call Hamiltonian simulation. The idea is that we want to, given a Hamiltonian H, we want to replace it by some other Hamiltonian H tilde, and we want to reproduce basically all the essential properties. And as early as 1981, in the famous lecture by Feynman, this sort of simulation of Hamiltonians, which in the physical language means simulation of physical systems, is considered an important motivation for quantum computers. Moreover, the idea of simulation is analogous to the fundamental idea of reductions between problems in classical computer science. So it's a very important primitive, potentially for quantum complexity theory. And it has also been argued recently that this kind of quantum simulation is one of the more realistic applications for noisy near-term quantum devices. Now let's be a little bit more precise. What do we mean by simulation? Well, one possible definition is what we call full spectrum simulation, and this is recently formalized by Bravi and Hastings in 17, and Cubitt, Montanaro, and Piddock in 18. Essentially, the definition can be visualized by this diagram on the right. The idea is that if you want to simulate H, you want to take the entire spectrum of H, all its eigenvectors and eigenvalues, and reproduce it as a low-lying part of the spectrum of H tilde. And we also allow some kind of encoding between the eigenstates by usually local isometry. While this definition is necessary in order to reproduce all the static and dynamical properties of the physical system, for many purposes, it may be considered too strong because often one only cares about the low-lying part of the spectrum. But regardless of the definition of simulation you use, one very basic fundamental question one can ask is, when can we make the simulating Hamiltonian H tilde simpler in some sense? And to our knowledge, there has not been any rigorous analysis of the resource required for simulation so far. So our work initialized the study of the resource and required for simulation by considering the notion of sparsification. And this is the simplification of interaction graph in some sense. And in the classical context, sparsification has two natural goals. One is degree reduction, and that's basically you want to reduce the interaction graph's maximum degree to some constant. And it turns out that this is actually always possible by a simple construction where you take any high degree node in the interaction graph and you replace it with a cloud of vertices with adding some ancilla and adding equality constraints between the ancillas. And this is used by Diner in 2007 to construct probabilistically checkable proofs in the classical computer science, which is considered a very important result. And another natural task that we consider is dilution, and this is the reduction in the number of terms or edges. And this is sometimes possible, as we illustrate with this following example. If you consider CSP on the complete graph, where every edge forbids the appearance of two ones, then it's easy to see that the satisfying assignments are the bit strings with either Hemingway 0 or 1. You can replace the same constraints by a linear number of trilocal constraints, which basically use ancillas to count the number of ones. And you can see that this reduces the terms from n squared to n. Now, Hamiltonian sparsification is a notion that we introduced, which is basically the generalization of these problems where we look at quantum constraints instead of classical. And this is motivated by, for instance, it could be helpful in saving resources in quantum computation. You also make it easier to study complex hypothetical physical systems by enabling the construction of simpler models. And it also has applications in complexity theory. For instance, we can try to quantize Diner's proof for PCP to maybe construct quantum PCPs. And maybe it also helps for some notion of universality in Hamiltonians. So in the context of Hamiltonian sparsification, we ask the very basic question, is it possible to simulate Hamiltonian H by another H tilde whose interaction graph is degree reduced or diluted? One might guess that, like the classical case, we know that in the classical case, the degree reduction is always possible. Maybe it's also possible for the quantum case, and this turns out to be no. And this is our main result, which is a no-go theorem for quantum degree reduction. It turns out that it's impossible to reduce degree of some Hamiltonians to a constant if you assume that the interaction strength is bounded and the encoding behaves in a natural way, in a localized way. And this is in stark contrast to what we see in the classical case, because we know, degree reduction, you can always use it pretty often in complexity theory problems. Now, despite the negative result that we have, we also prove a complementary positive result that if you relax the constraint on the interaction strength, you can actually always reduce degree to a constant if you use the polynomially large interaction strength. And our third result is, again, a no-go result, unfortunately, for dilution. And we show that there's no efficient classical algorithm to dilute Hamiltonians unless the polynomial hierarchy collapses to its third level. And because most of our results are no-go results, we study these limitations on the relaxed notion of simulation. And because a relaxed definition makes the impossibility result stronger, this also strengthens our results. To that end, let me now introduce the notion of gap simulation, which we consider to be a more minimalist definition. And the only requirement here is that we want to simulate the ground state and also the spectral gap above them. The rest of the spectrum we don't care about. We want to simulate the ground state because, they encode the solution to the quantum problem. And often there are signatures for exotic quantum behaviors like topological order, for example. And we also want to simulate the spectral gap, also because of its physical significance. In the context of many-body physics, spectral gap is used to characterize quantum phases of matter. And also, in quantum complexity and computation, it is used to govern, it governs the efficiency of adiabatic algorithm, and it also tells us how well you can approximate the ground state by a thermal state. And the definition is visualized here on the left. Essentially, the idea is that we're interested in the ground space or quasi-ground space of the original Hamiltonian H. And we want to, and this is basically a set of eigenstates below some spectral gap gamma, and we allow some a spread of the eigenvalues, and we characterize that spread by some fractional number w. And the idea is that we want to reproduce this ground space P as a quasi-ground space of H tilde, which we call P tilde. And we also allow some potentially different energy spread. Now, there are two variants of the definition of gap simulation that we give. The first one we call coherent gap simulation. And the error of this simulation is characterized by a small number epsilon that we call incoherence. And the idea is basically that given any ground state in the original ground space, and if we add some ancillary state, it should basically look like a ground state in the new Hamiltonian. And we also allow a more general definition where we allow some kind of encoding between the ground states by some isometry. We also consider a second, weaker definition that we call incoherent gap simulation. And here the error is characterized by a small number delta that we call unfaithfulness. Unlike the previous definition, which preserved all coherent superpositions of the ground state, the only requirement here is basically that given any ground state in the new Hamiltonian P tilde, if you decode it and reduce it to the original register, it's roughly contained in the original ground space. So this is basically what happens in classical degree reduction, for example. Now, well, the first one definitely implies the second one, and it's probably considered more correct because you transport all the quantum properties to the new Hamiltonian. We also show that when the ground state is unique, the two definitions are basically the same. Now let's restate our main result more formally in the context of gap simulation. Essentially, we prove that it is impossible to reduce the degree to a constant when we assume that the incoherence is a small constant. In fact, we can also prove that it's impossible to incoherently degree reduce when the unfaithfulness is small. And we assume that the interaction strength is bounded, and also that the encoding is localized in the sense that the isometry V maps each original particle to a constant number of particles. However, notice that we allow any number of extra ancillary qubits or terms. So in principle, you can add an exponential or doubly exponential number of qubits. It will not change the impossibility. Now, to get some intuition for the result, we'd like to illustrate the conceptual idea by proving a simpler, easier, weaker result, where we show that it's impossible when the incoherence is 0. So the proof uses a trick that we call contradiction-by-energy. So we consider the example where you have basically a complete graph interaction, all-to-all interaction, where we forbid the appearance of two ones. As we mentioned earlier, the ground states are easily shown to be the state with all 0 or states with 1 excitation. And it's also easy to see that the spectral gap here is 1 and the energy spread is 0. Now suppose that we want to gap simulate it with some other Hamiltonian H tilde A, then by the definition of gap simulation, that means that if we add some ancillary state to the ground states, these states must have energy 0, and if we add an ancillary state to a doubly excited state, they should have energy at least gamma. However, it turns out that if we assume that somehow H tilde A does not interact the pair of qubits I and J, this will imply that the energy of the doubly excited state is actually 0, and obviously this is the contradiction, which implies that you cannot degree reduce unless, because you have to interact basically all pairs of qubits. Now let's go through the last part a little bit more slowly. Suppose that H tilde A does not interact some pair of qubits. That means that we can basically decompose H tilde A into two terms, H tilde minus I and H tilde minus J. And what I mean is that H tilde minus I acts on everything except for I, so it commutes with all the observables on I, and similarly for H tilde minus J. Now the definition of gap simulation tells us that there's some energy constraints on the encoded ground states and the doubly excited states. And it turns out you can write the doubly excited states, the energy of the doubly excited state in a suggestive form. So let's proceed with the derivation. So let's first take this assumption that we have and plug it in. Let's expand the parentheses into two terms. And notice that on the left term, xi commutes with xj, obviously, because they act on two different particles. And xi also commutes with H tilde minus I, because that's our assumption. So you can actually commute through and annihilate the other xi. And you can do the same thing for the second term. And now let's replace xi with h tilde minus I with h tilde a minus h tilde minus j, basically using this relation. And then you can do the same thing for the second term. Now notice that we can actually reorganize the term in a way where we combine the h tilde minus terms together, and that gives you the energy with respect to the zero excitation state with respect to the new Hamiltonian, and the rest of the terms are the energy of the single excitation states. So apologize if you have gotten a little bit lost, but essentially the point here is that if you can write the doubly excited state's energy as a linear combination of the single excitation and zero excitation states. And as we said earlier, these have energy 0, and here we have a contradiction. Now, what happens if we allow epsilon to be positive? Well, we run into a little problem because those allowing epsilon to be positive will introduce these error terms on the order of epsilon times the norm of h tilde, and that can be very large if h tilde is polynomial and epsilon is constant. So it doesn't quite work. But we would like to prove the result where we allow a small and constant epsilon, and that requires some new innovation. So now let's go back to our main result where we showed the previous statement is true even if we allow epsilon to be a constant. And here we, instead of relying on contradiction by energy, we use something called contradiction by correlation. And this relies on a result in 2006 by Hastings and Coma, who showed that if you have a Hamiltonian with a gap between the ground space and the rest of the spectrum, you can show that the observables in the ground state must have decaying correlation. And if we look at our example Hamiltonian, it contains ground state of the form 1i0j plus 0i1j, so some kind of bell pair between any pair of qubits I and j. If you look at this corresponding ground state in h tilde, you will see that this gives a correlation of roughly 1/2 for every pair of particles. However, if you look at the right-hand side, if we assume that h tilde is a constant degree Hamiltonian, that means that there must exist two observables whose supports are at least distance log n apart. And obviously this is the contradiction because 1/2 is not less than some number that vanishes, and therefore it's impossible to reduce the degree to a constant for our example HA. Now you might ask, okay, this HA is not very interesting, it's a classical Hamiltonian, maybe it's an artifact that we want to preserve all the coherent superpositions. And it turns out that that doesn't really matter because there's another Hamiltonian who has a unique ground state, and this ground state is highly entangled. It's known as a Dickey state in atomic physics, and it's a superposition of all strings whose half of the bits are 1s and the other half are 0. And this state also has very large entanglement and correlation between every pair of particles. So using this, we can also show that it's impossible to even incoherently reduce the degree to a constant, assuming small unfaithfulness. So this is very different from classical world. Now, despite the negative result, we have a positive result as well that complements our earlier statement. Basically, our result is pretty tight because if you relax only one of the constraints, which is that the interaction strength is bounded, if you allow it to grow as a polynomial with a system size, you can actually always coherently degree reduce with a small assumption that you have to assume that the spectral gap is at least 1 over poly, but this assumption is natural in the context of gap simulation. Now, notice that naive constructions using perturbative gadgets in previous work typically require exponential interaction strength. To get around that problem, we use a sophisticated combination of standard tools in quantum complexity theory, specifically given an input Hamiltonian. What we do is that we look at the corresponding phase estimation circuit, and this is the unitary UPE that take given any input that's the eigenstate of the original Hamiltonian with energy E and some ancilla initialized to 0. You will map it to the same eigenstate, but now the ancilla has the energy written down in binary to some precision. Now, in the context of circuits, degree reduction is pretty trivial because you can simply use swap gates and ancilla to reduce the number of gates that acts on every qubit to a constant. So then you can apply the well-known Feynman-Kitaev circuit to Hamiltonian transformation to get a constant degree h tilde. We also applied an extra trick where we penalize the energy bitwise once the energy is written down, so that we reproduce all the eigenvalues of the original Hamiltonian H. Our proof, even though it works for gap simulation, it also works actually for full spectrum simulation. And there, we don't really require anything about the spectral gap. And this is also true if you restrict the output Hamiltonian to be a 1D or 2D Hamiltonian. Now, we're ready to wrap up the degree reduction stuffs and discuss a little bit on dilution. And our main result here is that there's no efficient classical algorithm because such an algorithm will imply that the polynomial hierarchy collapses to its third level. And the basic idea is that we use a lower bound in communication protocols, proved by Dell and Van Melkebeek in 2010, to show a lower bound for dilution. And actually, the proof is mostly classical because the counterexamples we use are classical Hamiltonians. So the setting of the communication protocol is as follows. Suppose you have a player who has access to some polynomial time Turing machine and is given some input, x, and is allowed to communicate with the oracle with unbounded computational power, and together they want to work together to find the answer to the decision problem to be either yes or no. And the resource you want to minimize, the cost of the protocol, is the number of bits communicated from the player to the oracle. Now, Dell and Van Melkebeek showed that if you give the player vertex cover problems on k-uniform hypergraphs, if you're somehow allowed to solve the problem with n to the k minus xi bits for any positive number xi, this will imply that co-NP is inside NP poly, which will imply the polynomial hierarchy collapse, which is unlikely to be true. So our result is simply a very simple application of this result, because the existence of a dilution algorithm will allow the player to take the vertex problem, cover problem, encode it as a Hamiltonian with n to the k terms, pass it through the dilution algorithm, getting a h tilde with n to the k minus xi term for any xi larger than 0, and communicate that to some log n bits precision, and decide the problem because the oracle can simply diagonalize the Hamiltonian, find the ground state, and tell the player how many what is the smallest vertex cover, for example. So this is not likely to be true because it will imply the polynomial hierarchy collapse. Now, does our result imply anything about the major open question of quantum PCP? In classical PCP reductions, constructions, degree reduction is commonly used. So can we rule out degree reduction in the quantum PCP context? And it turns out it's not quite, we can't really do it yet. And the main problem is that there's a fundamental difference between what PCP cares about, which is not the spectral gap, but the promise gap. The difference is that the spectral gap is the difference between the lowest two eigenvalues of any given Hamiltonian, but the promise gap is the promise difference between two classes of Hamiltonians, the yes instances and the no instances. And they're very different. Now, there always exists a trivial Hamiltonian. If you know the eigenvalue of the original Hamiltonian, you can easily construct a one local Hamiltonian that has the correct eigenvalue. So there's no way to prove impossibility of existence without restriction on further restriction on the reductions. But if you only consider constructive reductions, which we call reductions that basically map assignments to assignments, or in the quantum language, it means map states to states, we can prove that it's impossible to actually degree reduce or dilute for zero or polynomially small incoherence, and this is the same trick that we used earlier, the contradiction-by-energy trick. Nevertheless, I think that this doesn't really say much, because in the PCP context, we mostly care about constant incoherence, constant error. And we can't really extend the result to that context, because we can't really use contradiction by correlation, because there's no guarantee about the spectral gap. So I'd like to wrap up my presentation by concluding with a summary. We define gap simulation, which is a relaxed version of Hamiltonian simulation where we only care about the low-lying parts of the spectrum. We've also initiated the rigorous study of the simulation resources by focusing on the new notion of Hamiltonian Sparsification. And our main result is that in stark contrast to the classical world, there's something fundamentally different about the quantum world where generic degree reduction is actually not possible. And of course, there are many further open questions that arises in this research direction. For example, what about other simulation resources like alphabet size? And how about geometric restrictions, where we also assume that the interaction strength is bounded? And also, another question is, when can gap simulation be useful when full spectrum simulation is not possible? And obviously, there's some technical questions like, can we strengthen our results in the quantum PCP setting? And also, can we prove unconditional impossibility of dilution without computational hardness assumptions? And that's it. Thank you.
Okay, so thanks for that really nice talk. We have plenty of time for questions. Okay, whilst the mic's going to, do I have a mic runner somewhere? No, I have to do it. Okay.
Have you thought about Hamiltonian densification? I can motivate that if it's not clear why that's interesting.
Can you motivate it a bit more?
Well, yeah, so I mean, there's this intuition in physics that really highly connected Hamiltonians are well approximated by a mean field theory, that is to say a product state ansatz. Right? So one way you might try to get good approximations to properties of Hamiltonians with low entangled states might be to try to take a bare Hamiltonian, replace it with a simulating Hamiltonian that's denser, and then apply a product state to try to get some properties of that Hamiltonian. So have you thought about densification of Hamiltonians at all? I mean, I'm guessing not.
I mean, not. I guess we haven't really thought about that much because I guess there's always a trivial option of adding some, if you roughly know the properties, you can add some trivial terms or just extra ancilla. But I guess to kind of improve the properties so you can use this kind of mean field approximation or dynamical field theory, you would probably need some kind of special structure. And the problem we imagine is not always possible either. But we haven't really thought about it much.
Yeah, I know that there are graphs that can't be densified. So I don't know if that has any bearing on whether or not Hamiltonians can't be densified, but there may be some obstructions.
I think that probably under some natural definition where I guess if you, assume that it's not some trivial densification, then probably there exists Hamiltonians where you cannot be densified as well.
The question over there.
So you mentioned degree reduction method that uses phase estimation circuit and Feynman type Hamiltonian.
Yes.
Does this method give you local encoding?
Yes. It's actually trivial encoding. So the original state is the qubits stay basically where they are, and the state is essentially the same, except you add some ancillary state, which is no. Does that answer your question, or?
Yeah, I think so.
Okay.
So I have one question about your first no-go theorem. You need, in the conditions of the theorem, you assumed that each qubit of the original system got mapped to some constant number of qubits. Does it matter if those subsets overlap, or
no?
It still goes through.
Yeah, it still goes through. You actually can allow any constant depth circuit. Actually, we can relax the constraint to basically allow any log n depth circuit. Basically, we allow any mapping where each original particle is mapped to log n particle, and that also rules out any degree reduction.
Okay, thanks. Any further questions? If not, then let's thank Leo again.